This is Jack Jackson. Today we're going to be introducing the tangent function of an acute angle via right triangle similarity. As is typical with many of my videos here, these are going to be following along using the sketch, Geometry Sketchpad sketch, Trigonometry Ultimate that I have put together. And this one is the tab called Trig Ratios, you can see there. And this follows along with a class project that was discovery learning that we worked on in class in groups. So this is going to actually do the same construction using Sketchpad. So what we're going to start with is we're given some angle, and you can change this angle here, say to 30 degrees or whatever. And I like to start with, just like the project that we had in class, start with a 40-degree angle. So we start by just drawing a ray. And this ray was going to be called ray BA. Okay? And so B is going to be the vertex of our angle, and we're going to rotate around 40 degrees. Now the way to do this in Geometry Sketchpad, let me just to show you that, is you would mark B and say mark that, go to transform, mark that as the center, and then click on this angle, say transform, mark that angle, and then click on this here and say transform, rotate, and that'll rotate and give you that angle. I already have that set up here so that when I click this button it will do that. Now of course when you're doing this by hand, what do? You take your protractor, you set the center of your protractor here at B, you measure out the angle that we desire, in this case 40 degrees, make a mark, straight edge, and now you have your 40-degree angle. So everything in this is going to be based on this 40-degree angle. Now the next thing we want to do is pick a point D on this ray. We can pick this point anywhere on this ray, so we have free choice here as long as we're on this initial ray. And the next thing we want to do is we want to draw a perpendicular line from here. Now in Sketchpad I can just click on this point and this line here and say construct a perpendicular line, and it'll make it. Okay. However, how would you do this with your protractor? Well, you would set your protractor right here with the D at the center. You'd find where 90 degrees is up here, make a mark, and then draw a line in here. And what we want to do is we don't have to draw the full line in or a full ray in that. All we need is to find where it intersects this point up here at point E. Now again, we have free choice anywhere along here, but we have a right angle here at D, and the E is this other point here. And so there's our blue triangle, triangle BDE, with a 40 degree at B and a 90 degree angle at D. So what does that make the angle at E? Well, you should have figured out it's 50 degrees, which we could measure that, and we'll see that it's 50 degrees. Now what if we repeat this process for a different triangle, and we pick another point F? It could be bigger way out here, it could be closer in here, it doesn't matter, we can go either way. But now we have another triangle, I'll put it out here, the red triangle, and this one we pick a point F, make a perpendicular there, and this point up here is the point G, and now we have two triangles. What do you notice about these two triangles? Well, they're actually similar triangles. How do we know that? Well, remember what we looked at before. If we can get two of the angles to match up in the triangles and be congruent in corresponding pairs, then the third angle has to be congruent and the sides are proportional, and that's what we mean by saying the two triangles are similar. So obviously angle B is actually in both triangles. In one triangle that's angle EBD. Remember, we name triangles by 3 points, the middle one being the vertex, the first one being on one side, the middle one being the vertex, and the third one being on the other side. So this is angle EBD, or angle DBE, or angle GBF is the same angle. It's actually the same angle. It's this angle here. It's not just the corner there. It's actually these two rays, or the amount of rotation there, which is 40 degrees. So they have one angle that they actually share that's the same angle, and then here we also have two different angles, EDB and GFD, or since there's no confusion, we might just talk about angle D and angle F, and those are right angles, so that means that the other angles are the same. And so we get actually congruent angles, and those other angles up there are congruent as well. And then we also get some proportional sides. So if we measure the sides, here's what I've got them measured at the moment. Let me make some easier looking numbers to work with. Suppose we put this at 5 for BD, and I'm going to put this out at 10 here, approximately 10. So what if we notice, if this was exactly 10 and this was exactly 5, then everything that we have here in the second triangle should be exactly twice as big as what's in the other one. So that's our proportionality constant as we get that. Now, would everybody get the same thing here? Well, no, because we had choices here. So even if D is still 5, for example, from B, then this could be twice as much. It could be half as much. You know, it could be a factor of 0.5 here, which would say that the red triangle, the lengths, corresponding lengths are 0.5 or half as much as they are in the bigger triangle. Or they could be out here somewhere where they're 4 times as big, 3.94. Somewhere out here we reach 4 times the size of the other one, or it could be, you know, could be any number here. Of course, if it's D and F are the same, then this proportionality constant is actually 1. So we're going to get the same ratio of corresponding sides. If we divide the 8 by the 5, we get 1.6. The 6.7 by the 4.19, we get 1.6, and so forth. And if you see on these measures, this is actually using these measurements to compute it. So these really are doing the division. Okay. So there's our basic setup. So let's go back and just review a little bit. We started by let's hide some things here. So we started by just drawing a ray, using our protractor to make the given angle, which is 40 degrees. We pick any point we want, and we make a triangle. And it doesn't really matter where we make that triangle. We can get sides that are proportional. Now, let's hide these steps. Let's see, hang on a minute. We've got to hide some things here. Hide. Okay, so there's 1 through 9. And step 9, it says you should have noticed that no matter where points D and F are placed, the initial ray, the 3 ratios of a corresponding sides are the same. However, changing them also changes a different proportionality constant. So we're going to hide these steps now. Now, that's our basic setup. Now what we're going to do is we're going to define the tangent function. And look what happens here when we take our opposite side. So you've got, in a triangle, you have 2 legs and you have the hypotenuse. We can use that terminology for any triangle, but especially that's used for right triangles. So the longest side is the hypotenuse. Now, of your 2 legs, one of those legs is adjacent to the angle B, and one of those legs over here is opposite. So we're going to label the length of the, let's say we just hide the blue triangle and only look at the red triangle. Then this Y is the opposite side, and X would be the side from B to F that's the adjacent leg. Notice the hypotenuse is also adjacent to B, but we don't call that, that's not one of the legs, so that's the hypotenuse. The tangent doesn't have anything to do with the hypotenuse, it has to do with the two legs, and it's the ratio of those two legs. It's the length of the vertical one, well, it's the length of the opposite one, y, which right now, let's get our measurements back. Okay, and that's FG here, and we divide it by BF, this one here. So let's go ahead and try this with our calculators. So if you pull this up with your calculator, you can try this yourself. Take FG, which is 6.77 at the moment, divide by 8.06, that should round off to 0.84. And now if we look at the blue triangle and look at the measurements on it, right now BD is 5 and DE is 4.19. DE is the opposite leg, and BD is the adjacent leg. So this is your X, and this is your Y, the vertical one, and the horizontal one is X. And so we're doing Y over X, so it's 4.19 divided by 5, and that's 0.84. Over here we had the 6.77 on the top, and we divided by 8.06 to get 0.84. Notice you get the same number, and notice it doesn't matter where we put this. When we do that division, we get the same number. So they're both changing, but they're changing at the same rate, so they're canceling out. So this constant here is 1.33. That's our proportionality constant. Okay? So if we think of the triangle here, roughly this one is x1 and this one's y1, and this one is y2 and here is x2. If we do y2 divided by y1, well, remember y2 is just some constant, that proportionality constant times y1. On the other hand, y1 is that proportionality constant. Should be x1. No, it shouldn't be. It should be x2. So we're taking y2 and divided by x2. That's a right angle. This was our 40 degrees that we started with. But the constant is how many times bigger this side is than this side. That's k. And so we divide those. Y2 divided by x2, that's the same as k times y1 divided by k times x1. Look at that, what happens. The k's cancel, and you get y1 over x1. So it doesn't matter what your two triangles are. The proportionality constant basically just cancels out. So what happens is it doesn't make any difference where we pick this. We get this same number out for this ratio. Well, let's think back to our algebra classes. In our algebra classes, when we had some kind of situation where we had an input that gave us a single output, we had a name for that. We call that a function. And so this is a function. Okay, it's called the tangent function. And instead of calling it like f of x or g of x, we're going to call it tan of x, or, well, not of x, tan of, let's call it theta. Okay, and oftentimes we'll use a Greek letter, theta, spelled that way, looks like this. Kind of like an O with a line through it, theta. And oftentimes we'll use a Greek letters for angles, particularly theta gets used a lot. So the input is an angle, it's the measure of an angle, and then the output is this ratio. And of course the input is our 40 degrees, and there's the output. So that we see that the tangent of 40 degrees is 0.84. So if you did this and were able to measure very carefully, you should be able to get 0.84 for the correct answer. Okay. Now to get 0.84, you have to be very careful and draw this very carefully. Make sure that you measure things correctly and work this out. Measure very carefully for the lengths. Measure very carefully for right angles, and of course then you can divide. Now, what if you had to figure this out without a calculator at all? Well, we could do it We just want to be careful when we do our dividing. Now right now, taking 3.57 and dividing by 4.25, that's not so easy to do by hand. We could do it, but it would take a long time. But if we made something easy to divide by, what's the easiest thing to divide by? Well, the easiest thing to divide by would be 1. But 1 may make this too, say if it's 1 centimeter, it might make this too short to measure very accurately. So probably the next easiest thing to divide by is 10. So I would take this and draw this out here so that BF, which is x, is 10. And then look what happens when you do that. I can't get it perfectly 10. Let's pretend that's 10. And then when you divide by 10, you're just dividing this vertical distance by 10. Here it's 8.4 is the distance. Divide by 10 just moves a decimal point over 1. Real easy to do that. And we get 0.84. So notice it doesn't matter which triangle we look at. So we might as well just draw the one triangle, the red triangle, and we can find the tangent of that angle. Okay? Notice tangent uses the two legs. It's the length of the opposite leg, opposite your original angle, divided by the length of the adjacent leg. It does not use the hypotenuse. So if we oftentimes will do this in such a way that we'll orient our drawing so that we have a horizontal side to our triangle here, or one of our rays is horizontal. If so, then we can label that horizontal one as x. We often label horizontal distances as x, and remember from your algebra classes. And we can label the vertical distance as y. So again, we often label vertical lengths as y, and so we're dividing y by x. This should look like something that you already remember. If you put this on a coordinate grid, when you're going from point B to point G, the y is your vertical change and the x is your horizontal change. So you're dividing the vertical change by the horizontal change. That's the slope of that line, or the line containing that ray or that side. So the slope of that line is the tangent of that angle. Assuming what? Assuming that we have our bottom side here, our adjacent leg is horizontal. So isn't that pretty cool? So, and we're going out to the right here. Okay, so we have a positive slope. So there's an introduction to the first of the trig ratios we're going to do, which is called the tangent function. Let me stop the video there, and then we'll come back and look at sine and cosine in our next video.